Okay, so the record is on. Let's revisit this. As I have mentioned, we have 7 weeks before the midterm exam, and we have one national holiday on February the 16th. If you decide to take the holiday, you will not have the reading week, okay? But if you decide to sacrifice this holiday here, that means if we are going to have the class on this day, you will have 1 week free before the exam. Otherwise, I am obliged to teach this and perhaps give you the homework very close to it, and you're gonna have the exam coming up right away. That's what it is, folks. But we have a choice. We can sacrifice this holiday to get more free time before the exam. And of course, you're gonna have more time to submit the homework and have the graded one in return as well. For the second part, aside from the Songkran break, we have 2 national holidays again. But in this time, we are a little bit lucky because the second part is longer. And if you decide to take both holidays, again, you will not have the reading week. But if you decide to sacrifice only one, just one, right here, if you sacrifice one, you will have the reading week. So I will leave it up to you, okay? But let's say if you don't sacrifice any holidays at all, keep in mind that, you know, I may have to squeeze you to do the homework quicker, because otherwise I don't have time to grade it and return it to you before the exam. Okay, so that's the issue about the timetable that we are going to have this semester. Okay, for the hair now, oops, not this one, sorry. Yeah, the course portfolio, this is pretty simple that you guys should be used to this by now. This is CVE338. And here, just to give you the knowledge of the analysis of the indeterminate structure, mainly in this class. So the synopsis is that we're going to have to study the system of the building in basic, especially the system for the vertical load, because that's where most of the indeterminate problems are, okay? And the degree of freedom, and then you will be introduced to the displacement, and then these methods which are based on the displacement, okay? And this is the course learning outcome. If you are interested, this is the direct relationship with competence of the EU classes. And then, you know, I don't have the hobby, maybe I will add that in the future. And generally, this is the grading for this class. Keep in mind that the CVE341 is not finalized yet in terms of percentage, but I have the number from the Untitled, but this is not that class, so let's skip the talk about that, okay? This is the hours that we use, and you know, the plan has been mentioned in the timetable, so that's it, okay? And you guys should be familiar with this already, the rubric, okay? The third year student should be familiar with what we use in CVE 337. Senior citizen, you know, you should be familiar with this already. So it's been like usual. If you want to know ahead of time how you have to perform, you can study how you are going to be graded. And if you meet this rubric, you're going to get the points accordingly. Okay. So generally, yeah, it is what it is. I may come back and revisit this when we have the examples. Okay. All right. So that's the basic stuff that you need to know. So I'm not going to ask you yet what your decision is going to be, but now you know the problems with the holidays that we have on Wednesday. We are very lucky this year. So keep that in mind, and say we're going to we're going to make a decision maybe, you know, before the holiday comes. Okay. So now you see that this is the first date. Now we're gonna have to do something already. I begin with the degree of freedom and displacement and lateral load system and so and so. But I've been thinking about it this morning, and I'd like to maybe begin with the lateral load system first because you know, say it gives us the better idea why we need to understand the degree of freedom and so and so. Okay, so let's say, you guys ready? This is the beginning of the class. You ready?
Yes, yes.
Okay, thanks a lot. Now, PIs again. So let's say we have a building. Looks like a box like this. Okay, so let's say this is the outside of building. We have a building like this. And if I put an emphasis on a floor, it's any floor like this, perhaps. Yeah, line should be here. Better drawing, you know. If you have a better feeling about the drawing, you should understand the topic more. Okay, so let's say if I look at this floor, the top view is going to give you the floor plan, correct? And say in this floor plan, you may have the series of beams. Let's make it nicer. Okay. Floor plan. Okay. Same color here. And this is the top view, so we call it floor plan. And you may have secondary beam and so and so. So you can perform the analysis on the load from the structural analysis number 1, right? So it's gravity. So the floor plan, things like this, is designed to handle the gravity load or the vertical load. Okay, but let's say the purpose of having the structure, especially for tall buildings, is that you must also handle the lateral load. So when the lateral load comes in, this floor plan doesn't help anything, right? Because let's say if I'm crazy enough to draw the side view, this is only what you're going to see with the floor, right? Side view of the floor. So the lateral that comes in at the line of the floor is like this, right? So you see now that the floor itself cannot handle the lateral load. Are you with me? If you look at each floor individually, it's like a flat plate like this, and then the load comes in. The plate is just gonna go. So the floor system alone is for taking care of the vertical load system or the gravity load. When you have the lateral load, you need to have the lateral load system to handle the lateral load itself. And floor alone is not enough. So generally, we need to have some system. Floor system itself is not enough to withstand the lateral load. Okay, so you need to have the floor working together. So from the floor plan that you see here, the side view, if we can integrate all the floor system to work together, we are going to have the system. Okay, so I can say that therefore integrated system is needed. Yes. Okay, so let's say from this picture, if I can put the floor together, you know, and let them work together with the columns, we're going to have what we call the framing system, correct? So this is the system of members working together to form the lateral system, lateral load system. So now if the lateral load comes in at each floor, we can now have the system to withstand it. Okay, but just take a look at the system itself. Now let's say we begin with a very typical system like this. Let's say no floor, just one frame. But in general, let's say it's a fixed support like this. Now, in the past semester, you would know that you will have a lot of reactions, right? Because this is a fixed support. So how many reactions are we gonna have? 1, 2, 3, 4, 5, and 6. Okay, 6 reactions. So that means if we are going to use the force method, we're gonna have to determine the degree of redundancy and then come up with the number of equations to eliminate the degree of redundancy, right? So say if the force method is going to be used, it means that you have 3 degrees of redundancy, and so 3 compatibility equations is going to have to be established. Okay, and it's not going to be that straightforward. And this is just an example of a frame with 1 floor and 2 columns. So let's say, what if you have a system like this? What if the system is more complicated, which is the real world, right? Who's going to build the building with 2 columns? No, you cannot have the building with 2 columns, right? So in the real world, let's say you're going to have something like this. Okay. So say now you have 15 reactions, right? 3 at each support, and you have the good old 3 equilibrium equations. So this one becomes like 12 degrees of redundancy, and you need 12 compatibility equations, okay, to solve just the reactions. But to make the matter worse, who's going to build the frame with just a roof? You need floor, right? So the real building is going to be something like this and more. say it like that. Let's say I add one more floor. Okay. So now, do you think, just let's take a look at this frame. Do you think this frame has the same number of redundancy as this one? Junior. I'm not asking senior, because if you don't answer this one, if you cannot answer this one, you may be a little bit embarrassed. Okay. Junior, do you think this one has the same degree of redundancy as the one on the top?
Yes.
Thank you for answering. Any more answers?
No.
Yes. No, not the same, or no answer.
No, at the same.
Not the same. No, not the same. Okay, thank you. You know what? The answer is no. Let's take a look at this. Let's say this one, you have 15 reactions, correct? 3 at each support. So let's say we already have 12 degree of redundancy due to the reactions alone. Now let's say you cast your magic spell and you can solve all the reactions. If all the reactions are now known, okay, if all the reactions are now known, and I cut the free body diagram here, and I cut the free body diagram there, my free body diagram would look like this, right? I have the reactions, which I already know. What happened next? I also have the unknowns coming out of the free body diagram. 6 more, right? With the reactions being known already, you cut the free body diagram at the green line. Now you have 6 internal forces coming out, and yet you still have only 3 equilibrium equations. So that's going to add 3 degrees of redundancy more. Are you still with me? So it's 3 more here, 3, 3, and 3. So it's 12 more internal degree of redundancy. You can say the pink one is the external, but the orange one is the internal. So this one, because we add more floor, you should expect to have more unknowns, right? So in the end, we have like 24 degree of redundancy. So the force method is out of the question. Nobody is going to be crazy enough to do that. Okay, let's say this is the frame system. Let me try to simplify the problem and look into the floor. Okay, let's look at this floor. Sometimes, you know, people can build the beams as simple beams. It depends on what kind of structure you are going to use. If it is a steel structure and you know, all the members come in pieces, we may choose to connect, you know, the pink beams here as a simple beam to the blue one. But say in concrete, it's easier to cast them all at once. So you may have the floor that has the beams that is continuous, like this. Okay, let's say I can give you the support, this one as a support, or that, and that. Okay, so now let's say I can look at the beam. Now, because I have so many supports, I can draw the beam and we have 5 supports, right? Like this, 1, 2, it's too close. 3, 4, and 5, okay? And in concrete structure, it's a lot easier to cast this beam at once, not breaking it. So you end up with the structure that looks like this. See, now instead of trying to look at this huge structure with so many degrees of redundancy, I am now focusing on the beam, okay, on the floor first, and then I'll go back to the frame, okay? So this one you can see, let's say we are not gonna bother with the horizontal force, okay? Because if you talk about the beam, generally we are talking about the gravity load. So let's say we have the load like this. So we're not gonna be bothered by the horizontal force. So let's say you have 1, 2, 3, 4, 5 vertical reactions. So let's put it in here for the sake of clarity. So you have 6 reactions. You have 3 degrees of, you have 3 equilibrium equations. So this structure becomes 3 degrees of redundancy. Okay? So I'm just gonna try to demonstrate to you once why the force method is gonna give you such a crazy life. Okay? So if this is a 3 degree of redundancy, and we are not gonna be bothered by sigma fx anymore, it means that we need to have 3 compatibility equations, right? So let's say this is our structure. So 3 compatibility equations are needed. So if you can recall, we can establish that by removing reactions so that we have what we call the primary structure, right? So let's say I'm gonna do that. I'll try to draw the same beam. I remove this one, that one, that one, and that one. So this becomes my primary structure. Okay, let's say you can name this A, B, C, D, and E. Now when you remove this, when you no longer have the support, you will have the displacement instead. Let's not draw that one, right? So your beam is going to come down like that because you no longer have the support. And this will be your delta at B. This will be your delta C. This will be your delta. That delta in the wrong way. How do you, it's delta. Okay, yeah. What did I do with that one? Okay. Yeah, this one is also wrong. It's funny. I got, okay, right? And then what you have to do is now you have to apply the unit load at the location where you remove your reaction, right? So you apply the unit load at B. But the craziest thing, now you will know why you need to have like 2 subscripts. Because when you apply the unit load at B, this will become delta B, small b, caused by load at B. This will become delta C caused by load at B. This will become delta D caused by load at B. And then you keep doing this. Oh. Now you apply the unit load at C instead. So now you have delta B caused by load at C, see? Delta C caused by load at C, and then delta at D caused by load at C. And you do the same with D. And afterward, you can only write the equation that delta B plus, this is due to the RB, right? So it's delta BB multiplied by RB plus delta BC multiplied by RC plus delta B by D multiplied by RD. This is equal to 0. That is one equation. Okay, and you keep doing the same for the rest to come up with 3 equations. So it's pretty crazy. And the fourth method, let's say, is say it's not viable for you to use anymore. And most importantly, computer program cannot handle the fourth method because it cannot create the primary structure. Or maybe it can, but to write the computer program to create the primary structure seems absurd. So we don't do that. And keep in mind that we need to build something like this in the real world. So the fourth method is not an option anymore due to the demand from the structure. So that's why in this class, you are going to learn the new method, which is based everything on the displacement. Okay, so it is important that you learn how to identify the displacement of the structure. Okay, so let us start by taking a look at the displacement. Say, my son complains that my voice is too loud and he's having a quiz, you know. So I'll try to lower down my voice a little bit. Okay, hopefully that you can understand. But you know, I have to go full blown, otherwise I cannot talk. I cannot speak in the class with just whispering voice like this. Okay. So anyway, now let's start from the beginning. Okay. The definition of degree of freedom is in the handout, I suppose. Oops, sorry. So you can find it somewhere. That's the degree of redundancy. That's the old one, the force method. Here's the displacement method, and hey, that's the old one. Okay. The let's why do I have this one? That's the old stuff. Yeah, okay. This is the new method. Why I said? Sorry, I thought that I could find it easily. Actually, I didn't plan to visit this one. But anyway, it doesn't seem like I have this with me. But now you know that you have to determine what we call the degree of freedom instead of degree of redundancy. Okay. Here, it's only here that say, okay, determine the degree of redundancy. Oh, sorry, that's the wrong one. Anyway, so let's not look at this. What we need to know, sorry, my apologies. What we need to know is the degree of freedom of the structure, because we are going to use the new method that will handle this more efficiently and more beautifully by solving for the degree of freedom. Okay, so degree of freedom by definition is the displacement of the structure that you need to identify. Once you can identify all these displacements, you would be able to, you know, describe everything you need to know about the structure. Okay. So let's come back to the note, and let's say, if you can think of the support like this. Right. He's too young to handle things by himself. So sorry. Okay, so let's say this is a hinge. A hinge will have two reactions, right? So it can rotate because you don't have the moment restraint. So a hinge will have the degree of freedom as a rotation. And for the roller can also move in the horizontal reaction because it has a vertical reaction. So the roller will have the degree of freedom of 2. That is the horizontal displacement and rotation. For the fixed support, it has 0 degree of freedom because there's no movement on the fixed support, right? And you may say, yes, we determine the degree of freedom of each joint. So when we come back and look at this particular continuous beam, yeah, this is called a continuous beam. You know that we have 1, 2, 3, 4, 5 rotation. And because of the beam, we don't have the horizontal force. We may neglect the horizontal movement. But if you want to include that, you will say, okay, I have 1, 2, 3, and 4 degree of freedom. So it's correct to say 9 degree of freedom. Okay, so now we can go back and take a look at the frame, starting from the simple one. How many degree of freedom do you think this frame has? The top one? Oh, quiet. How many degree of freedom, folks? This is a joint, right? So it can move horizontally, it can move vertically, and it can rotate. And likewise for this joint, 1, 2, and 3. So this frame has 6 degree of freedom. Okay? What about this one? This one has 1, 2, and 3 at one joint. 1, 2, and 3 at this. 1, 2, and 3, 1, 2, and 3, 1, 2, and 3. So this one has 15 degree of freedom. Okay? The question? What about this? Can you answer now? I should erase this one because it's green. Hello, would you like to try? Hey, are you still with me? Thank you very much. Yes, because we have 10 joints, right? And 3 degree of freedom at each joint. So that makes it 30 degree of freedom. Thank you very much. Okay, so you count like 1, 2, 3, and then 1, 2, 3, and then so on and so forth. So this one has 30 degree of freedom. Okay, and let's say degree of freedom with the new analysis method that you are going to undertake, it's a lot easier to handle than trying to solve for 24 degree of redundancy. Okay, and ladies and gentlemen, because what you will learn in this class predominantly is the displacement method. We are going to solve these displacements. So you better be able to identify degree of freedom correctly from the beginning. failure to identify degree of freedom from the beginning to solve the structure is fatal. Okay? Is it too much for the first day? Huh? Hello? Is it too much? What is the thumbs up mean?
Yes.
Yes, it's too much. It's me.
Yes.
Yes, it's too much. Okay, so why don't we have the first break then? How about that?
Good idea.
Okay, so let's have a 10-minute break and then come back on maybe about 10:35, okay?